For lesson number 2, I'm going to discuss Fourier half-range expansions. If f of x is piecewise continuous on the closed interval 0 to L, then f of x can be extended into an even periodic function, capital letter F, with period 2L, so that f of x equals capital letter F of x on the closed interval 0 to L. The resulting function has a Fourier series equivalent to that of a cosine series. Similarly, f of x can be extended into an odd periodic function, capital letter F, with period 2L, so that small letter f is equal to capital letter F on the closed interval 0 to L. The function f, capital letter F, has a Fourier series that is a sine series. This process of extensions is called cosine or sine series half-range expansions. Now let's discuss the concept of even and odd functions you studied in calculus. On a half interval 0 to L, we can represent a function as a series containing just sine terms or just cosine terms, whichever we choose. We can do this by exploring the properties of odd and even functions. The function f is said to be even on the closed interval negative L to L if f of negative x is equal to f of x for all x in the closed interval negative L to L. The graph is symmetric about the y-axis, and the integral from negative L to L with this f of x dx can be re-evaluated, using this integral. So 2 times the integral from 0 to L of the function f of x dx. Okay, so y equals x squared is a parabola, which is an even function because y equals square of negative x is x squared, which is equal to the original function. Also, cosine function is known to be an even function because cosine negative x is the same as cosine of x. This is the graph of a parabola y equals x squared. As you can see, this is symmetric about the vertical axis. So when you integrate the whole area of the parabola, you may consider just 1/2 0 to L. Now since the graph is symmetric, you can multiply the area of this by 2. And then this is the graph for cosine function, which is symmetric about the vertical axis. The function is odd on the closed interval negative L to L if f of negative x is negative of the original function. The graph is symmetric through the origin, and the integral from negative L to L f of x dx is equal to 0. X plus x cubed is an odd function because negative x plus cube of negative x is negative of the original function, negative of the quantity x plus x cubed. Sine x is known to be an odd function because sine negative x is negative sine x. So this is the graph of x plus x cubed, so symmetric about the origin. Okay, so the area, let's say here, the area here is the same as the area to the other side of the vertical axis, but this one is positive, This is negative area, so when you get the sum, okay, the integral would be 0. So this is the graph of your sine function, which is symmetric about the origin. Okay, let's discuss the arithmetic combinations of odd and even functions. We summarize the product of odd even. So an even function multiplied by another even function, the resulting function is even. When you multiply two odd functions, the resulting function is an even function. Even times odd or odd times even, the resulting function is an odd function. We can apply this concept in simplifying the evaluation of the Fourier coefficients. So for example, if f of x is even, okay, you can write a sub o as 1 over 2l, 2 over l from 0 to l, f of x dx. And take note that this is even. So this is even. Cosine is known to be even. So when you multiply, you get an even function. So this is even multiplied by an odd function. So even times odd, you get an odd function. So when you evaluate, okay, when you evaluate a sub n, okay, now since this is a sub n is 2 over L, so we evaluate from 0 to L, f of x cosine n by x over L dx. So take note that this one is even, okay, even multiplied by even, so this one is an even function. And since b sub n will give you f of x times sine n pi x over L, this one. So this is an odd function, therefore the integral from negative L to L will be equal to 0. So automatically for an even function, your b sub n will be 0. So no need to compute or evaluate the coefficient for b sub n. And when f of x is odd, okay, so you have, okay, this one is odd. We know that cosine is even, so the resulting function is an odd. And this one is odd, okay, multiplied by another odd function, you get an even function. So automatically, the integral from negative L to L, f of x dx will be 0. So it follows a sub o and a sub n automatically will be 0 when you have an odd function. And we just evaluate your b sub n from 0 to L, so multiplied by 2 over L, f of x sine n pi x over L dx. So the Fourier series will contain only the sine function, and for an even function, the Fourier series contains only the cosine function. Okay, so to summarize, the Fourier cosine series is an even extension of f of x to negative L to L. If f is integrable on 0 to L, then the Fourier cosine series of f of x on 0 to L will be f of x equals a sub o plus summation from n equals 1 to infinity a n cosine n pi x over L. To take note that your b sub n is equal to 0. Okay, so we just evaluate your a sub o, a sub n. Okay, when you have, if you want to extend the function to a cosine series. And then the Fourier sine series is an odd extension of f of x to negative L to L. So if f is integrable on 0 to L, then the Fourier sine series on the closed interval 0 L will be as follows. So this is your f of x that contains only sine function and your b sub n, because your a sub o, a sub n is equal to 0 when you have an odd function. Okay, so we just compute for b sub n, which is 2 over L, and then integral from 0 to L. F of x sine n pi x over L dx. So n will take the values 1, 2, and so on.